chemistry. So when we left off last time, we talked about reading the periodic table, taking the information from that table and using it to figure out how many protons, neutrons, and electrons an atom has for that particular element. We then talked about whether or not those atoms would be happy or not based on how many electrons are in their valence shell. If an atom has fewer than 4 electrons in its outermost shell, or if it only has 1 and it only has 1 shell, it may choose to gain or lose electrons. If that happens, if it loses electrons so that it can end up with a valence shell that's full, then it becomes an ion. If it lost electrons, that gives it a positive charge because it has now more positive protons than negative electrons. If another atom grabs those loose electrons and gains electrons, it's gaining negative things, negative electrons, so it ends up with a negative charge. It is also an ion. If we take those ions and we put them in a solution, we call that an electrolyte. So electrolyte solutions have ions in them. You probably drink electrolyte solutions from time to time if you've ever had something like Gatorade or Powerade. Those are kind of salty tasting solutions because they have ions in them. So those are those electrolytes. Your blood is a giant electrolyte solution. You have lots of ions floating around, including calcium, sodium, potassium, and so on. I had you draw electron diagrams. We use the rule that the first orbital can hold 2 electrons and every orbital after the first can hold 8. You have to fill earlier orbitals before you can go out further. Think of it like building a skyscraper. You have to have a basement before you can have a first floor. Then you need the first floor before the second floor, and so on. And then we actually did some practice with that. And here's just a demonstration of if I have an atom that loses an electron, like sodium, then another atom can grab that electron. And the atom that lost the electron is called a cation. It's got a positive charge. Just think the T looks like a plus. And the atom, the chloride that gained that electron, is now an anion. So I left you last time with an assignment. I asked you to draw again the electron configurations for practice for the atoms here that are circled in green. So hydrogen, potassium, calcium, oxygen, and chloride. And we did something similar to that last time, but I asked you to do it yourself, so let's see if we can do those. So we had hydrogen, potassium, calcium, oxygen, and chloride. So we have hydrogen, potassium, calcium, oxygen, and chloride. So hydrogen has an atomic number of 1. So we know that in the nucleus, it's going to have 1 proton. And that means if it's electrically neutral, it's going to have 1 electron. Let's take a look at potassium. Potassium has an atomic number of 19. So that means we're going to have 19 protons in the nucleus, and we're going to need 19 electrons. So we'll put 2 in that first orbital. We'll fill the second one with 8. So now we're at 10. Make another orbital with 8. So that will get us to 18. And that means to get to 19, we need just 1 more in the outermost shell. There. Now we have an electron configuration for potassium. This one is hydrogen. Calcium, if we pop back over there, calcium has 20 for an atomic number. So that means it's going to need 20 protons in the nucleus. and it will need 20 electrons. So let's draw that out real quick. So that's 10, 18, and 20. Oxygen has an atomic number of 8, so we will have 8 protons in the nucleus, and we will need 8 electrons. So that's 1, 2, 3, 4, 5, 6, 7, and 8. And then chloride, if I remember correctly, has an atomic number of 17. So we will need 17 protons. So then we'll draw in the electrons here. So that's 10. And 17. So now let's see what would happen to these atoms in order for them to become happy or stable. Now again, we are going to be keeping things really simple. There are a lot of complicated rules as to when certain atoms will interact with others. So we're just going to use an example. So if we take a look at oxygen down here, he only needs 2 more electrons. So we could stick a hydrogen there and another hydrogen there. These 2 hydrogens are now happy because they each have 2 electrons. And my oxygen is now happy because its valence shell is full with 8. And we have created a molecule of water. Now if we look at the other 4 atoms that we have here, chloride only needs 2, so it could do something similar to what oxygen did. Oh, sorry, chloride only needs 1. So it could do something similar, and it could share with a hydrogen atom. But let's hold off on that for a minute. Over here, we have hydrogen. Hydrogen could share with something like oxygen or chloride, or hydrogen could share with itself. And then we have a molecule of hydrogen. Potassium and calcium both have problems because they have less than 4 electrons in their outermost shell. So they're going to need to lose that electron, and calcium is going to need to lose both of these electrons in order to make their outermost shell one of the shells that is full. That's going to mean that since potassium lost 1 electron, it's now a little bit positive. It lost a negative. Calcium lost 2 negatives, so that makes it even more positive. So both of these turned into cations. Chloride now could have shared with hydrogen or somebody else. Or it could take these kind of loose electrons that are floating around, and it could just borrow those or use those for itself. Oh, it only needs the 1. So now chloride picked up this loose electron, which made it a little bit more negative because that electron is negative. So chloride now turned into an anion. Now, the next thing that we're going to talk about is bonding. So there are lots of different types of bonds and attractions within the chemical world. I'm going to focus really on 4 big ones. So when we look at bonds or attractions, there are 4 main types that we are going to be concerned with. The first is called a covalent bond. Now, a covalent bond means that you are sharing a pair of electrons. You can have different types of sharing. So you can have a polar covalent bond, or a nonpolar covalent bond. A polar bond means we have unequal sharing of electrons, and a nonpolar bond means we have equal sharing of electrons. Now the way I remember that is I just think that when I think of the Earth, there's a North Pole and a South Pole, and they're not remotely the same. Polar bears are up in this hemisphere, penguins are down in this hemisphere. There's a lot of differences between the two poles. So what I want you to drill into your brain from here until the end of the semester and really the end of time is that when you see the word polarity or polar or polarization, anything with polar in it, you should think difference. Okay? Now, nonpolar is when we have equal sharing. So let's take a look at our polar covalent bonds and nonpolar covalent bonds. So when we look at this diagram that we just did here, if you can ignore my scribbles a little bit, we have a couple of different covalent bonds. There's a covalent bond down here and here between the hydrogen and the oxygen, and there is a covalent bond here between the two hydrogen atoms. Now what happens is, when you have an atom that's really big, it's like a bigger planet. So I like to remember I said think of these atoms like planets. You've got your protons and neutrons that make up the planet, and then you've got satellites orbiting around, and those are your electrons. So if we think about a planet, the bigger the planet, the stronger the gravitational pull. The more it's going to pull in on things, right? So if I have two atoms that are of exact same size, I have two planets of the same size pulling on these electrons. So they're going to pull equally, and remember we said equal is nonpolar. So that means that this is a nonpolar covalent bond. And really, the only true nonpolar covalent bond we can get that's completely nonpolar is between two atoms that are identical. Now, if I have one planet that's really big and one planet that's really little, the big planet is going to pull on those electrons harder. So what happens is we end up getting polarity or a difference. So down here, between the oxygen and the hydrogen, we have polar covalent bonds. Over here and also over here. So what happens is these electrons get hogged by the oxygen. And that results in some differences within the molecule so that my oxygen has a little bit more negative charge than positive charge because he's kind of hogging these negatives a little bit more. So my oxygen ends up being a little bit negative. Now this little squiggly D means a lowercase Greek letter delta, which means partial. Since my hydrogens don't get to see their electrons very often, when I look at them from this angle here, I'm mostly seeing that proton, so hydrogens end up a little bit positive. So we end up with a molecule that's a little negative on one side and a little positive on the other side. Now water is probably the most important polar substance that there is. So when you think of polar, I want you to think difference, and I also want you to think of water a lot of the time. Okay? All right, let's go back here. My second, or really now at this point, third type of bond is an ionic bond or an ionic attraction. Now in the chemistry world, the only really true bond is a covalent bond, and there are lots of different types of covalent bonds. We are going to use covalent bonds to build all these really big molecules within our bodies. In particular, all of the organic molecules that we will be talking about in a little bit. An ionic attraction, or in the biology textbooks they like to call it a bond, this is an attraction between opposite charged atoms or molecules. So it's an attraction between opposite charges. So if we go back to the drawings that we just did, we created a potassium ion, a calcium ion, and a chloride ion. So this positively charged potassium is going to be attracted to this negatively charged chloride, and they're going to form an ionic attraction. Now, polar covalent bonds are physically sharing electrons, so they're kind of like the marriage of the bonding world, right? They're sharing a house, they're sharing a mortgage, right? It's more difficult to break them apart. Whereas ions are just really, really hot for each other. All I have to do to break them up, though, is put them in a liquid in water, and I can separate those ions from each other. So ionic attractions are very strong as a solid, but they're very weak in a liquid, which is convenient because we have lots of ions floating around in our bloodstream. And that water that makes up about 67% of your body keeps those ions apart most of the time. Now, if you're really dehydrated, those ions might be able to find each other, lock on, and then we start to form crystals, and the next thing you know, you have something like kidney stones. The last type of attraction that we're going to talk about is a hydrogen bond or hydrogen attraction. Now, this is similar to ionic. It's an attraction between opposite partial charges, and one of those atoms has to be hydrogen. So it's an attraction between opposite partial charges where one atom is hydrogen. So let's take a look at what that looks like. So if I take a water molecule, for example, we have an oxygen and we have two little hydrogens, right? And we said that the oxygen is hogging the electrons that they're sharing. So that makes my oxygen a little bit negative and my hydrogen's a little bit positive. But now if I have another water over here, and my hydrogens are a little bit positive, and the oxygen is a little bit negative, now what we have are positive and negative partial charges that are also going to be attracted to each other. So that is a hydrogen bond or a hydrogen attraction. Now, these are kind of like, you might wonder what a partial charge means when I'm looking at these little squiggly Ds. When we think about something that's charged, I like to think of magnets. So if you think about your refrigerator, most people have magnets on their fridge. And every time you shut the door, some of those magnets fall off. And other magnets, if you want to get them off the fridge, you have to like scoop them to the edge and then pry them off. So think of the ones that are really attached to the fridge as being the full charges, and the ones that fall off every time you shut the door are these hydrogen attractions. So these are very, very weak in solution. But what happens if we turn water into a solid? Well, that bond gets longer, right? Water expands, and it gets incredibly strong. So if you leave your soda, for example, in the fridge or in the freezer for too long and it freezes, the water in it expands and your can of Coke or whatever it is explodes. Now, you are about 67% water. So why is that relevant? Well, if the water in your cells were to freeze, it would expand and physically rip apart those cells. And essentially that's what happens when you get frostbite. All right, so that's our summary of bonds, and I think we'll leave it at that for right now. and we'll come back and talk more about chemistry in a little bit.